Good morning, good morning, good morning. Hope everyone's doing all right. Sorry for running a few minutes behind. Got caught up trying to secure the house. We got a little bit of a storm coming, so we got stuff outside. So when I looked up, saw the time, and I know I couldn't cancel class because so many of you look forward to all this mathematics that we get every morning, right? Every other morning. So yeah. Let's see. I think everybody's in. Everybody's in. Okay, cool. So hope everybody's doing great. Everybody's doing all right. Did anybody have any questions or anything or general questions before we look to get into lecture today?
Today's the last day for homework, right?
What you mean? Which homework?
Chapter 2.
No, it goes till 7-11. It should be 7-11.
Oh, did the date change on the
On my math lab?
Yeah,
It should
because
not
the last time I
have.
checked, it said 8 on there.
All right, let
No,
me check.
it's till 7-11.
Oh,
Yeah.
okay.
The 8 you might be thinking about, you might be thinking August 8th. Yeah, I think that's the only 8 that's up there, but that August 8th is just that like that final date that's out there that I can't flex on. And
Okay.
so I think chapter 3 and chapter 4 right now says August 8th because as we get past the section, I'll change that date according to where we are. But yeah, so for chapter 2, it should be 7-11, which is this Sunday.
Okay, thank you.
Yeah, no problem. Thank you for asking.
I was also wondering if you saw my email about the chapter 2 homework assignments.
Let me see. You sent it yesterday evening?
Yeah, I think so.
Let me see. Okay. Yeah, I'll respond to that today.
All right, thank you.
Yep, not a problem. Before the day is out, I'll respond to it. All right. Because I just read part of it. That's a personal question, not a general class question, right?
Right. Yeah.
Okay. Yeah. Okay. So yeah, I'll respond to it.
Okay.
Yeah. All right. Anybody else? Anything else before I get into the lecture? Everybody good? Everybody straight? All right. Cool. Let's see where we left off. All right, we did. Yep, I remember doing that. 91. Okay, so we're looking at 3-5 today. Let me look at 3-6. What's 3-6? Quadratic. Okay. All right, so let's start with 3-5 today. Last class we covered 3-4. We're up to 3-4. And of course, if I'm saying something that your notes say different, let me know. But I believe we covered up 3-4. So we're looking at rational functions and their graphs. All right, first thing in that section or in this section is asymptotes. So asymptotes are places where the function is undefined or does not exist. Another way to look at it is places where your graph does not cross. All right. There are 3 types of asymptotes, and we'll look at how to find those. So we have the vertical asymptote, horizontal asymptote, and the slant asymptote or oblique. Slant and oblique asymptotes are the same thing. All right. Of course, if I scroll up and you still copy and let me know. So the first one, vertical asymptotes. That's going to be where the denominator is equal to 0. The way we find our vertical asymptotes, so we're going to simplify our expression as much as possible. Then we set the denominator equal to 0 and solve. All right, so first example, or the first type of problem that we will be held responsible for is going to find the vertical asymptote is if any. All right. So want to simplify as much as possible. There's nothing that can be simplified here. When we look at our denominator, if we factor it, nothing can cancel out. So there's nothing to simplify there. So now we'll take the denominator, set it equal to 0, and then solve. So you're talking about x squared minus 9 equal to 0. I decided to factor that into x plus 3, x minus 3 is the difference of squares. X plus 3 equals 0, x minus 3 equal to 0. I have x equal to -3 and x equal to 3. So right here is just a rough sketch of what that asymptote would look like, or not the asymptote, what that graph will look like. And what this is saying is that we have two vertical asymptotes, one at -3 and then one at +3. So that's where our graph is not going to cross. Notice it creates three separate graphs in our function. Oh, what does that mean? All right, my pen dropped and hit a button. Everybody can hear me okay, right? Can I get just one person to say, I hear you?
Yeah, we hear you.
Okay, cool, thank you. Appreciate it, because like I said, my pen dropped, hit the button. I saw some stuff pop up, then it disappeared. So I just want to make sure I'm still connected to you guys. All right, so notice we have two vertical asymptotes, one at -3 and one at +3. The function would actually create three separate parts where they do not cross, -3, and they don't cross +3. So that's just a rough sketch of what it would look like, but yeah. So that's what happens when we have our vertical asymptotes. Before we go to the next one, everybody okay? So we have these vertical asymptotes at -3 and +3. All right. Next one, we have g of x is equal to x plus 3 over x squared minus 9. All right, do it like that. So remember I said the first step was to simplify as much as possible. So that's what I did right here. I factored out my denominator again, which is x plus 3, x minus 3. And we see the x plus 3 cancels. And that leaves us with this expression right here as with 1 over x minus 3. So what I want us to do is take note of the little notes that I've written here. Now we cannot ignore the x plus 3 in my denominator was still a part of my original equation. So that's what I wrote in the green, is that the x plus 3 produces a restricted value, but the x minus 3 that's left produces an actual vertical asymptote. So because x plus 3 canceled out, it does not produce a vertical asymptote, but it's still a restricted value. In other words, the function does not exist there, but the x minus 3 is what produces a vertical asymptote. And so that's what I have here. In the green, you see x equal to -3 is a restricted value. In other words, that's a value that cannot be used. And then x equal to 3 is a vertical asymptote. All right, so if anything ever cancels out, that's going to be a restricted value. Whatever's left in your denominator would be a vertical asymptote. Hold on one. Any questions on B? All right, looking at C, we have x plus 3 over x squared plus 9. So x squared plus 9 cannot be factored. No, in order for us to factor that, it has to be x squared minus 9. And then you see here that if I were to go ahead and solve that, subtract 9 from both sides, then take the square root of 9. a -9, excuse me. That'll give us plus or minus 3i. Those values are imaginary, so that means there is no vertical asymptote. No vertical asymptote. All right, any questions? All right. Go to the next one. Everybody good? All right, so let's look at a horizontal asymptote. So we're going to let n be the degree of the numerator, in other words, the highest exponent in your numerator on your variable, and let m be the degree of the denominator, which is the highest exponent on your variable in your denominator. So if n is less than m, in other words, if the highest exponent in your numerator is less than the highest exponent in your denominator, your horizontal asymptote is y equal to 0. If those exponents are equal, then you're just going to take the numbers that sit in front of that variable in each case and simplify that, and that will be your horizontal asymptote. So the leading coefficient of your numerator over the leading coefficient of your denominator. And notice for our vertical asymptote, we had x equals. For your horizontal asymptote, we have y equals. So that does matter. And then if n is greater than m, the degree of your numerator is greater than the degree of your denominator, there is no horizontal asymptote. And then we will go to our slant asymptotes, and we'll talk about that when we get there. But there is no horizontal asymptote produced. All right. Any problems before we go ahead and make that happen? All right. So find the horizontal asymptote if there is one. So the original, oh, didn't we do that? So this is our original equation, f of x is equal to 4x over 2x squared plus 1. So putting it back, my the exponent, the highest exponent on my variable in my numerator is 1. Highest exponent in my denominator is 2. So here we have our first scenario. If the highest exponent of our numerator is greater or less than the highest exponent in my denominator, then my horizontal asymptote is 0. That's y equal to 0. All right, any questions on that? So the next one, 4x squared over 2x squared plus 1. So we see that our exponents are the same. So what we'll do is take the coefficients, the number that's sitting in front of those variables, 4 and 2, and use those as a fraction. So it'd be 4/2. Simplify that, the horizontal asymptote is 2. All right, any problems? Then for the last scenario, the exponent in my numerator is greater than the exponent in my denominator. So that means no horizontal asymptote. All right, any questions on anything I've said up to this point? All right, so let's look at slant asymptotes. All right, so when n is greater than m, that last scenario we had, the degree of our numerator is greater than the degree of our denominator. There should be a slant asymptote. So we're going to use long division or synthetic division, excuse me, or synthetic division if possible to find our slant asymptote. And it will be in this form. You know, remember whenever we did long division, we had our quotient plus the remainder of what we're dividing by. So slant asymptote will be, you know, this part right here. You leave that remainder piece off. Any questions? Any questions? All right, so they ask us to find the slant asymptote. Here we have x squared minus 4x minus 5 over x minus 3. So because of the setup of our denominator or our divisor, we can use synthetic division. So that's what I did here. Remember, we use the opposite sign here. So that's what I have, a positive 3 in my box. Then we use all of our coefficients down over here. So that's 1, -4, -5. Bring down 1, 3 times 1 is 3. Add those together, it gives me -1. 3 times -1 is -3. Add those together, and then I'll have -8. So we write down the result 1 degree less than what we originally had. So that's why we have x to the first power minus 1 plus -8 over x minus 3. And my slant asymptote is going to be this part right here. So that's why I have y equal to x minus 1. Once again, your horizontal asymptote has x equal, I'm not horizontal, your vertical asymptote starts off with x equal, horizontal asymptotes start off with y equal, and notice our slant asymptotes also start off with y equals. All right, any questions? All right. Here we have g of x. We have x squared plus 1 over x minus 1. First thing we notice is that we have a missing term, our x term. So we put a 0 here as a placeholder. All right, I decided to use synthetic division again. So positive 1 right here in the box because I have x minus 1, and then my coefficient is 1, 0, 1. Drop 1 down, 1 times 1 is 1. The 1, 0, 0 plus 1 is just 1. 1 times 1 once again is 1. Add those together, we get 2 as a remainder. And that'll be x plus 1 plus 2 over x minus 1, which means my horizontal asymptote is just the x plus 1. All right, any questions? No? So any problems before we go to 3.6? That's all that 3.5 was about. Your asymptotes, vertical, horizontal, and slant. All right, go to the next page. Everybody good? Let me see what 3.7 was. Okay. So let's at least do part of 3.6. Let me see 3.7. Yeah, 3.7 is okay. So I may do part of 3.6. I don't know. Let's just see. Let's just see. All right. So 3.6 polynomials and rational inequalities. So we've dealt with linear inequalities before, but now we're looking at polynomial inequalities. So we can talk about quadratic or higher, and then rational inequalities. So now starting off with quadratic. Notice here we have our two scenarios that are parabolas, of parabolas that could be produced by quadratic equations. Notice that you have these spots where your parabola crosses the x-axis. That's going to be where your equation is equal to 0. Everything above that is positive. Everything below that is negative. So whether you flip it or it's right side up, concave up, or concave down, everything above that, those 2 points are positive. Everything below those 2 points are negative. So that's going to matter when we look at setting up our intervals and everything like that. Over here is just emphasizing or re-emphasizing what our inequality symbols are, what we will be using: less than, greater than, less than, equal to, greater than, equal to. All right. So first one, we have 2x squared plus x is greater than 15. First thing we want to do, just like if we had an equal sign there, we want to set one side equal to 0. We want to be able to compare our equation to 0. So we have a clean comparison. So we subtract 15 to both sides. 15 cancels out on the right. On the left, we have 2x squared plus x minus 15 is greater than 0. So basically, you want to know, when is 2x squared plus x minus 15 positive? If you're talking about greater than 0, you want to know when is something positive. And so that's why we want to set one side equal to 0, so you make a clean comparison to positive versus being negative. If it was less than, then you would want to know when is the equation negative, because that's when those are the only values that are less than 0, negative values. So in order to figure out when it's positive, we want to know when is the equation equal to 0. So we go ahead and substitute our inequality with an equal sign and solve it like we would any other quadratic equation. So I factor 2x squared plus x minus 15 into 2x minus 5 and x plus 3. Then set both parts equal to 0.
Can you go back up?
Yep, how far you need.
Keep going a little bit up. Just a little bit. A little bit more. Right there. So
All right, let me know when we can move forward.
I'm good.
All right, let me know how far. All right, so we good, good. All right, so we have these two spots where our equation, our function is equal to 0. So x equal to 5/2 and x equal to -3 is where our function is equal to 0. The reason why these are important, because remember, anything above those 2 points or greater than those 2 points, as far as our parabola is concerned, would be positive. Anything below those 2 points would be negative. All right, so that's going to help us to set up our intervals. So I just chose or just drew a generic number line so we can see how our intervals will be set up. So we're going from infinity to -3, -3 to 5/2, and then 5/2 to positive infinity. All right, so let me erase some of this stuff so we can walk through it. All right, so in each case, now you don't have to do this. It's just the best way to be able to keep yourself organized and to be able to have all your information in one spot. So when I say you don't have to do this, you don't have to set up a table or a chart. It is the best way to do it, but if you decide not to do it, then that's fine, but you still have to go through the process. So you might as well set up a chart to make the process as easy as possible. So just saying that because I've had people in the past say, well, do you have to do it this way? But you don't have to do it necessarily this way, but you do have to do these things in order to be able to establish your answer. All right, so like I said, hold on. Okay, cool. So like I said, here's my generic number line. Here are those intervals being reflected according to the number line. We're going from -infinity to -3, -3 to 5/2, 5/2 to infinity. And notice here, these are the things we want to establish. I've already established our intervals. We need some test values within those intervals, and then we're going to examine the behavior of our graph. Now, these intervals, we need our interval notation. So don't forget, for our infinity signs, they will always use parentheses. That will always be the case no matter what. Now, for our numbers, we have a choice between parentheses or bracket. What will dictate that is our original symbol. See, I wrote it right here. Because we have greater than, then we're going to use parentheses. Don't forget, it's the or equal to that we'll use bracket. So if it's greater than or less than, then we'll use parentheses. If it has the or equal to symbol, then that's when we know we'll be using bracket. Okay. So we'll use parentheses on our numbers. All right. So when we look at our intervals, we need test values for each interval because remember, the graph is going to respond a certain way for all of the values within that interval. Remember, everything above those zeros were positive, everything below produced negative results. So we need test values for each one of our intervals. It doesn't matter what you choose, just remember whatever you choose, you have to calculate with it. So I would choose something simple like -4. -4 is less than -3. So you choose anything less than -3. You can choose -100 if you want it. Anything less than -3 will still give you the same result. So anything in between -3 and positive 5/2, I would choose 0. 0 would be the easiest number. And then anything greater than 5/2, 5 divided by 2 is 2.5. So you could have chose 3 or you could choose 4. I think I chose 4. Yep. So those are my test values. Once again, you don't have to choose those exact test values, but you do need to choose something that's within each one of those parentheses, each one of those intervals. All right. So now we're going to plug in the test values. And I always use my factor expression. You don't have to, but it's up to you. But you do have to plug it into one of these two, either your original equation or the factor expression, or the factor representation of that expression. So, all right, so this is me doing that all 3 times. I took -4, plugged in where I saw x. Now, I don't necessarily need the number. I just need to know, is the number going to be positive or negative? So when I plug this in, I get a positive result out of the first, negative result out of the first parentheses. That's 2 times -4 minus 5. So that'll give me a -13. Then here, -4 plus 3 is also a negative number. So negative times negative is positive. Once again, if you want to go ahead and do the calculation and get out the number, that's fine. What I want to know is, what is the result? Is the result going to be positive or negative? Because that's going to dictate my answer. So we're looking at positive. Plugging in 0, I get negative times positive. So that'll be negative. And once again, just being generic here, because you could have came up with any number, but the bottom line is your number positive or negative? That's what's going to dictate our answer. And then for the last one, plugging in +4, I will get a positive number times a positive number, which would be a positive. So those would be the behaviors of our graphs within those intervals. All right, any questions? All right, so now we have our behavior and we go back to what we were trying to find out. When is the equation positive? So we go to our intervals. When do we have positive results? And that's when there's negative in the interval, -infinity to -3, and then 5/2 to positive infinity. And so that would be our answer. Use your union sign to join together your 2 different intervals. All right, questions before we do another one? All right, so let's look at another one. So here we have x³ plus x² less than or equal to 4x plus 4. And the first thing we want to do, just like before, is to set one side equal to 0. So I subtract 4x and subtract 4 from both sides of the equation, give me x³ plus x² minus 4x minus 4 less than or equal to 0. All right. So x³ plus x² minus 4x minus 4 is less than or equal to 0. This time we want to know, because it's less than, when is that expression negative? All right, so now I'm going to solve this. We set it equal to 0 to figure out when is this expression equal to 0. So you set it equal to 0 and then solve. So we have 4 terms. So I'm going to solve by factoring by grouping. Group together the first 2, group together the second 2. Out of the first factorization, out of the first grouping, I can factor out x squared. Out of the second grouping, I factor out -4. And that'll give me this result, x plus 1 times x squared minus 4. Then I also can factor x squared minus 4, which is the difference of squares, to x plus 2, x minus 2. So if I set each part equal to 0, that'll give me x equal to -1, x equal to -2, and x equal to +2. Any questions? Any questions? All right, scroll up. Everybody okay? So once again, let me erase this stuff in the chart. All right, so generic number line, using our solutions, our values where our equations equal to 0. So we see the intervals that we have set up for us. Negative infinity to -2, -2 to -1, -1 to 2, and then 2 to positive infinity. And that's what I have set up right here. All right. Now, just like before, infinity signs will always take on parentheses. Now, going back to our original setup, notice we have or equal to, so that means we need to use bracket on each one of our numbers. All right, any problems with that? All right, so now we need test values to test each interval to see what values, what is produced in each one of those intervals, whether it's positive or negative. I'll go blue. So -3, -1.5, we're talking about something within those intervals. You can use anything in those intervals. And these are things that I've chosen. I believe I did that, -3, 1.5, yep. Okay, I'm just trying to stick to what I did in my notes already. Any questions on the test values that I've chosen? Remember, you can choose anything within the test value, within the intervals, as long as you're willing to calculate with those, you'll be all right. All right, so now we need to plug those values into our function to see what type of result. Is it going to be positive or negative? So I use my factored representation of that expression, x plus 1, x plus 2, x minus 2, and plug in each one of them accordingly. There we go. So plugging in -3 in each spot that I see x. All right, end up getting negative times negative times negative, which is negative as a result. Plugging in negative 1.5, I got negative times negative, which gives me positive. Plugging in 0, I get positive times negative, which the result would be negative. And then plugging in 3 gives me positive times positive, which is positive. So I know what somebody may be thinking is, well, if you find out one, will it always alternate? Because that's what happened with the last one. For the most part, with the ones you guys will get, they will alternate signs, but there's no guarantee. And most definitely when you get into calculus, this is a foundational method that you can use in calculus to determine the behavior of your graphs and different things like that. They will not always alternate. It will not always alternate. So, you want to get in the practice of doing it right. Like I said, they should alternate with the ones that you guys will get, but there's no guarantee depending on what's going on in the function. Now, also don't just do one and then assume the rest of them will alternate, because if you made a mistake on this one, that means the rest of them will be wrong too, if all you're going to do is assume. So you do want to make sure you go back, check your calculations, and don't assume anything. All right. So if I go back to my chart, talking about negative, positive, negative, positive. All right. Anybody still copying before we go ahead and do the final answer? All right. So go back to our original. We want to know when is the expression negative. So that means here and here, these intervals will be our answers. So we're going from negative infinity to -2, -1 to +2 as our answer. Any questions? Any questions? All right, everybody good, everybody straight. Okay, so I got a text message while I was in class that I have to take my son to the doctor. It's not an emergency, so nobody has to be feel bad or be concerned, but I found out it's something I got to do. So this is a good place to stop. Also, that gives us room to not have to jump in and do anything outside of chapter 3 next class. So we'll finish off. Oh, what's going on with my notes? Okay, I don't know why that was happening. So we'll finish off 3.6 next class and then do 3.7. So that gives us a chapter and a half, a section and a half to do. Don't let me forget to start right here, guys, in 3.6. So if I jump into 3.7 next class, somebody stop me and make sure I do rational inequalities out of 3.6 first. And then we'll go from there. Any questions, concerns, comments before we close out today, go into the weekend? Everybody good, everybody straight? Don't forget, like your classmate mentioned, 7-11, this Sunday is our due date for chapter 2 stuff. So make sure you get that in there. Once again, if you have any issues with anything, if my math lab shuts down this weekend or something crazy, it happens before, make sure you let me know so I can address it accordingly. I won't know unless you guys tell me. Outside of that, I think that's it. So you guys have a great weekend, be safe, and I will see you on Tuesday.
Have a good weekend, sir.
Thanks, you do the same. Take care.
Enjoy your weekend, Professor.
Thanks, appreciate it. You
Good
do the
weekend.
same. Thanks, take care.
Have a good day, Professor.
Thanks, you do the same.